physics at the University of Tor Vergata, working on a scanning tunneling microscopy to study liquid-solid interface. Then she moved to Linz University at the Kepler University. After the postdoc, she moved to University of Florence, where now is associate professor. After this long journey, she is back in our institute to present a seminar on the interesting work she does on organic modeling. Giulia.
Okay, thank you very much for the kind introduction. It's really a pleasure for me for being here after such a long time. I've done here the bachelor and master degree, and then after I traveled a bit, and it's a pleasure today to present the last results of the last year that I've obtained at the University of Florence. Well, okay, so this is the right sense. Maybe we can that we don't. Yes. So this is Florence, and this is our laboratory at the Department of Chemistry, which is a little bit far from Florence, far from the city center. It's in Sesto Fiorentino, close to the airport, but we are in a nice environment. We have many ships that help us in research. This is the laboratory of molecular magnetism that has been funded by Dante Gatteschi many years ago, and now with a great job is held by Roberta Sessoli and Professor Andrea Caneschi, and their job is really to hold together a multidisciplinary team, all working in the topic of magnetism and molecular magnetism in particular. So there are people who carry on likely the chemical synthesis of our compounds, nanostructuration of nanoparticles. There are theorists, there are people who carry on the hardcore magnetism, so they do EPR, NMR, and speed magnetometry on the chemical compounds. And this is us working at the edge between molecules, the gas phase, and solid state. So we stick molecules on the surface. And this is the lab that actually now we rearranged, we reassembled a bit using a different transfer chamber. And here we have basically 3 halls concerning people. This lab is handled by Matteo Mannini, full professor at the Department of Chemistry, me and Lorenzo Poggini from CNR-Institute. And 3 halls concerning the instrumentation, because this platform, this USB platform, is capable to perform molecular deposition by thermal sublimation, but we also implemented an electrospray deposition method for fragile molecular structures, a scanning tunneling microscope working in a helium flow, so capable to go down to 40K more or less, and the photoemission spectroscopy part with XPS, UPS, and now we recently bought an inverse photoelectron-spectroscopy and also a low-energy electron diffraction suited properly for molecular systems that are quite new, so we still haven't used them so much. The most important thing is carried out at the synchrotron, because we need a magnetic characterization for our molecule, and this is done by, of course, preparing our sample in our setup in Florence and shipping them through a USB suitcase directly to the XMCD facility in Deimos at the Soleil synchrotron. This is the place in which we most often go for this kind of experiment, in which we can probe our molecular samples, thin films on surfaces, through an element selective technique in which we heat sample by X-ray light with circular right and left polarization, and this different polarization produce a different absorption signal as soon as we have a spin moment and also an orbital moment on the surface. So the difference between these 2 XAS signals corresponding to the two polarization give rise to this XMCD signal, to this dichroic signal, which is somehow proportional and gives a fingerprint of the magnetism of the sample. And this is for us is a really important tool. Of course, you can do that in presence of a magnetic field that is directed perpendicular to the surface, and in presence of very low temperature, nominally 2K if we use the CHROMAG setup, but we can go with the dilution pre-dilution cryostat also to the sub-K regime, so down to 200 milli-K nominally. We basically work with two different kind of molecular systems. From one side, the single molecule magnets, and this is the compound that I'll speak most about today. And the second one are molecular spin qubit. So sticking on single molecule magnets, these are tiny molecules, so one molecule is more or less 1 nanometer large, that hold in a single molecule a magnetic hysteresis loop. It's like a small magnet that doesn't need magnetic domains, as in the normal state, as in the normal magnets. So it's usually formed by a magnetic course embedding some transition metal ions or lanthanide ions, having a spin, usually a large spin number, and a strong magnetic anisotropy. And the combination of these two factors creates at very low temperature, very low depending on the kind of molecule, a barrier, an energy barrier that hinders the reversal of the magnetization. So our bit 0 and 1. So at low temperature, the magnetization of the single molecule magnet is blocked, and then we can observe an hysteresis loop associated to the single molecule or to a molecular layer that we have on the surface. Then this is also a quantum object. So we can observe these jumps in the hysteresis loop that corresponds to the quantum tunneling event, in which at some resonant fields like 0 or other resonant fields that depends strictly on the kind of molecule, we can have a tunneling of the electrons from one magnetic state, the down state, for example, to the up state. So we lose this magnetization behavior, this fixed magnetization behavior, and we start a resonant tunneling regime. And it's important to understand that because this is the key of the sensing of this molecule to the superconducting state. This is the topic that I mostly investigated. So why? First of all, investigating magnetic molecules, magnetism, and superconductivity. We know that magnetic fields interact in a quite nasty way with superconductivity because magnetic fields tend to align in the same direction the two spins of the electrons of the Cooper pairs that characterize the transport of the superconductor. But out of this nasty interaction, there are a bunch of very interesting phenomena that we can observe. For example, we can couple a ferromagnetic material to a superconductor, and we can try to inject, other than an electron current, a spin current that can then drive without resistance. Or from a local point of view, we can couple a single spin from a magnetic ion or from a molecule or from an electron of a radical, for example, with the Cooper pair, with the formation of a bound state that is visible as a localized state within the band gap of the superconductor. This is called the U-Shibarasimov state. And if we couple multiple Shiba states, we may achieve the Long-Sought-Majorana bound state, which are topologically protected states, and then can be used for reliable quantum computation. Then that's why we started to investigate molecules of different types on top of superconductors. As I mentioned before, I'll speak mostly about single molecule magnets, in particular this iron 4s methyl derivative, which has 4 iron ions with an anti-parallel spin arrangement with a total spin equal to 5. It has a large opening of the hysteresis loop in the milli-K regime. And we investigated this derivative on top of a lead-111 crystal, which is superconductor below 7K, roughly, and 80 millitesla. To characterize this molecule, of course, we, as a standard, we perform XPS characterization to confirm the integrity of the molecule, but also STM to see if this molecule can form ordered pattern on the surface. And the combination of our scanning tunneling microscope and images and density functional theory, we understood that we have this triangular arrangement in which this beloved structure is one single molecule, and one single molecule here is almost as this organic ligand that protect the magnetic core that is almost parallel to the surface. It has a deviation of 22 degrees with respect to the surface normal, the direction of these sulfur atoms that also represent this C3 axis, that represent the main magnetization axis of the molecule. So it's very important for us to know how the EC axis of the magnetization, so the main magnetic moment of the molecule, is directed on top of the surface. And then we performed, as I mentioned, the XMCD spectroscopy. So we probed that we got the expected fingerprint from the XMCD signal from the iron core, from the iron magnetic core. We used also linear polarization to obtain this signal that tell us that actually we have a high ordering of the molecule on the surface. And most importantly, we went at the energy of the maximum, the minimum of the XMCD, and we scanned the magnetic field at 200 milliK. So this showed a very large hysteresis loop. If you see the blue curve, this is the hysteresis loop that we record when we impinge normally with the X-ray and the magnetic field on the surface. We also simulated this curve, taking the proper Hamiltonian approach for this system, and we see that the system is actually characterized by a large hysteresis loop and by these two characteristic jumps that correspond to the resonant quantum tunneling of the magnetization that I mentioned before. This is very important because then we expect that the molecules behaves as it should in bulk. So where as soon as it feels zero field, then starts to lose its magnetization, start to resonantly tunnel between the up and down state. Then what we expect actually, for example, if we probe this on gold 111, is that the magnetization of the molecule, this is a zoom close to zero of the hysteresis, the magnetization of the molecule stay flat, constant, roughly constant, till field zero, and then start to do the resonant tunneling of the magnetization. Of course, when we have a superconductor, then an ideal superconductor, we expect that crossing below the critical temperature and below BC, so 80 millitesla for lead, we have the Meissner state. So the superconducting bulk screens out suddenly the external magnetic field, which is directed always perpendicularly to the surface. So we expect that all molecules at 80 millitesla, not at zero, start to perform this resonant tunneling of the magnetization. So we expect that the signal is actually quenched at corresponding at BC, at the critical field. Then what we observed this some years ago is that at BC, the magnetization, so the real data that we measure are the blue dots, the magnetization starts to decrease at BC, but it does it slowly with a linear trend. So we start to dig into the theory of superconductivity and actually rediscovered that the superconductors are not ideal. So this Meissner state doesn't exclude the field suddenly at once, but depending on the geometry of the superconductor, it does it by forming alternating superconducting and normal domains. So the superconducting domains in which the field locally is zero, then enlarge and expand linearly with the field by decreasing the field. So we have a linear increase of these superconducting domains, and basically what is going to happen is that we linearly increase the fraction of molecules performing quantum tunneling of the magnetization, and this explained also performed some simulation on that. This explains this linear decrease of the magnetization that we observed between the critical field and zero. And so this told us that, first of all, we can have a way, yeah?
What is the frequency at which you measure the hysteresis, these loops? Milliseconds, hours?
The rate is usually 0.03 Tesla per second.
No, the time, how much time for measuring these hysteresis loops?
The whole hysteresis loop?
Yeah.
I mean, the whole hysteresis loop.
The shape of the loop or independent of frequency?
It is independent on the frequency in the regime that we have, because of course the magnetization of the molecule has a decay, so it will last for some hours, but we are well below this time. So as you can a little bit enlarge, smooth or make more sharp these edges, this jump, when you go faster, but you don't see a decay that is due to the molecule. So that decay was actually due to the superconductor. So from one side, we had a way to control the magnetization of the single molecule magnet, but we also had a local probe for the superconducting field and for the transition. And we demonstrated this also on another single molecule magnet, that is the terbium PC2 molecule, in which a terbium ion is embedded between these two Dallas-Hahn ligands. And here also the magnetism, the hysteresis loop of the molecule is actually compatible with what we expected from the superconducting side, but I don't want to speak in detail about this because I want to show you today some new results that we had on the same iron 4 molecules that I presented to you before, but on more interesting superconducting platforms like type 2 superconductors having the vortex state. So in this case, these are the results that we got in the last year, so quite recent and still not published. Here we had a thick film, but quite ordered, of iron 4 single molecule magnet, so the same molecules that I mentioned before. And we are on an niobium diselenide type 2 superconductor, in which we have the vortex state below 7K. These measurements again are done at the mid-decay regime, and the BC2, so the second critical field, so the appearing of the vortex state at 3.6 Tesla. So we have that in all this regime, under the molecule, we have the vortex lattice appearing. Then we measured also the magnetization of the niobium diselenide without molecules to know that this niobium diselenide has a reversible hysteresis loop, that if you go to see what is happening at very low field, it has a strange opening of the hysteresis loop that now we are going to comment when we see the hysteresis of the molecules when we go close to zero. So now I'm going to zoom into the most interesting region for us, in which we have this strange behavior of the hysteresis loop that we measure as with the same method that I mentioned before on the iron 4 film. So what we have here is that when we scan the field from high field to lower field, we have more or less a constant trend of the magnetization that is similar to what we expect without the superconductor. But we know that there are vortices here, but the fact is that vortices are so dense that produce just a very tiny small oscillation with respect to the external field. So basically, the local field that the molecules explore is nearly the same of the applied field. So we don't see any strong deviation from the expected molecular behavior. Then, when we approach to this 30 millitesla, we have that at this point, the curve starts to deviate and to go down. So we then are exploring a second region of this hysteresis loop, in which the medium field of the vortex lattice is lowering as much as we lower the external field, but also it happens that these are calculations done on the average field fluctuation of the superconductor. We have that locally, close to each vortex, the magnetic field locally goes below 10 millitesla. So such a low value is already sufficient to make the quantum tunneling of the magnetization of the molecule happen. So in this case, we have a lowering of the signal because we have some molecules that start to perform this quantum tunneling of the magnetization. The more, this is a sketch of the vortex lattice that will be always less and less dense the lower is the magnetic field. So we arrive at a certain point that is roughly 15 millitesla. That is actually the BC1, the first critical field of the superconductor, in which we have the happening of the Meissner state. So in this state, we have that vortices are suddenly pushed out the bulk of the crystal. So we have a lot of molecules that are doing this quantum tunneling of the magnetization. But we also have the shielding, the screening Meissner currents that preserve the internal field. So the few vortices which are trapped inside the superconductor cannot exit anymore. This explains why our signal concerning the magnetization of the molecule doesn't go really to zero, but it stays with a low magnetization value at a constant height, let's say at a constant value between plus and minus BC1. So in this case, we have a few molecules which retain their magnetization because we trapped some vortices inside. Then what is occurring here in the fourth region, so below, when we scan the field farther below minus BC1, is something that has to be still understood from a molecular point of view, but it is really interesting. For sure, what we know that at minus BC2, when we go down, we have some anti-vortices, so vortices directed in the opposite direction with respect to those which are pinned inside, coming from the edges to the center. So at a certain point, these vortices should annihilate, encounter and annihilate the previous pinned vortices with the magnetization in the up direction. So what we assume here is that this annihilation vortex produce an energy that we roughly estimated that is compatible with the reversal of the magnetization by thermal scaling up the barrier of the single molecule magnet that led the up magnetization to turn to a down magnetization. Because what we observe here is that almost suddenly the magnetic signal from the molecule pass from roughly minus 5% to plus 5%. So we suppose that all the molecules with the up magnetization reverse their magnetization to the down magnetization. So this is quite nice because confirm that that molecules can also probe vortices and dynamics, including trapping and pinning. And we could also think about playing with with vortex annihilation to control the magnetization of the single molecule magnets. Another thing that we have recently done is to ask ourselves if the single molecule magnet, other than being just a probe for the superconductivity, can somehow influence the superconductor. To do so, we went to the Muon facility in Switzerland, in which we could heat the sample with a muon, and the muon in its decay that has inside the sample in the bulk emit a positron roughly in the direction of the spin moment within that encounter within the sample. So this technique is usually used to probe as a function of the muon implantation energy that scales towards the surface to the center of the bulk, is used to probe the depth profile of the internal magnetic field of the superconductor that from the edge, thanks to the Meissner state, has to decay, must decay towards zero when you go in the bulk. So what we have done is to use an niobium film to probe this decay by spectroscopy that we have within the superconductor, and to understand how this decay is changed or altered when we put molecules on top. What we have done is to use on top of the niobium film a layer, 7 nanometer layer of this terbium Pc2 single molecule magnet, which embed a terbium T+3+ ion with a magnetic moment and a J=6, and we saw that actually at the interface we have a sort of proximity effect in which we have an additional screening effect from the external field exerted luckily by the molecular layer. To understand, these are also very recent results that we hope to discuss soon with people in the field, to confirm that actually this shift was due to the magnetism of this object, of this molecular object. We put a 7 nanometer layer on top of niobium of yttrium Pc2 of the yttrium Pc2 analog. In this case, we have exactly the same molecule with 2009 ligand, but instead of the terbium 3+ ion, we have a yttrium 3+ ion with a J=0. So we have the diamagnetic analog, and we have actually just the paramagnetic properties coming from the electrons, from the unpaired electron delocalized on the phthalocyanide structure. What we observe here is that, as you can see here, at the interface, we don't have any strong shift of the internal field, but we have a case in which we replicate somehow the behavior we observe on the bare niobium. So we have to understand the reason why terbium Pc2, the magnetic momentum, is doing that to the superconductor. The idea now is that the dipolar field exerted by the terbium Pc2 molecule can be directed in the opposite way with respect to the external field, and then can screen out the field and help in this screening. But these are, of course, data and investigation that we need to rationalize further. So to conclude this first part concerning single molecule magnet, I just showed you that we have the possibility to sense the stray field and the local field of the superconductor, that we can also influence the screening properties of the superconductor. And of course, it would be interesting to test some of the hybrid devices in which you have magnetic molecules and superconductors coupled together. I then will briefly speak. I don't know how much time I still have. I can go till you are too bored. Okay. So I would like to briefly present you the second kind of molecular system that we investigate. That maybe could be also more interesting for this audience. That are the spin molecular qubit. In this case, on the contrary of the first system, we have usually an ion which has a low spin state. So usually we have a low spin number. So usually we have spin 1/2 system that we want to use a spin qubit, meaning that we want to control coherently the phase of the spin that, of course, can be used for quantum computation application, because we can use the linear combination of the up and down state to run quantum computing algorithms. Of course, here the power, there are some chemists, I think, around the power of chemistry is that we can tune the ligand properties with respect to single ions. We can tune the ligand properties, or try to in order to increase as much as possible the coherence time, so the time in which the molecule retain the spin phase, in order to allow more reliable quantum manipulation algorithms. What we can do, what chemists can do, is also, and this is very interesting for the new trend, is also to connect and to bind in a controlled way two or multiple spin systems. So we can have a ligand, like here you can see a single vanadyl tetraphenylporphyrin with a vanadyl ion, which is the spin 1/2 state. Here you see a dimer, a vanadyl 3-phenylporphyrin dimer. Okay, in which we can, through the backbone of the ligand, control which is the magnetic exchange interaction between the two ions. Then, of course, this would be very important when you want to process more complex quantum algorithms and you want to create some quantum logic gate. Then, concerning this spin 1/2 system, one of the most funny systems that we work with is this CPTI COT molecules synthesized by Giulia Soares group in Brazil, in which you have a titanium 3+ ion sandwiched between two carbon-based rings. This is a cyclopentadienic ring with 5 carbons, and this is with 8 carbons. The nice part is that you have a magnetic orbital impinging nominally potentially towards the surface, so in the DZ² orbital. And we measure quite a long coherence time that corresponds to 35 milliseconds in process solution, which is quite a high coherence time for being, and also in the panorama of qubit coherence time. The nice thing is that Giulia's group can also modify the ligand a bit, for example, to create this complex with the fluorenyl ligand that can have a better stick to the surface. Of course, this system can be sublimated at room temperature, so you just open the valve and let them fly on the surface. And we had a nice experience with our medium temperature STM, in which when we had this CPTI COT, this molecular layer on the Godwin-1 surface, we saw a quite ordered pattern with this alternating bright and dark row, and this bright and dark row were also changing as soon as we changed the bias. And then we started to ask why this was going to happen, and we were quite sure that we could have at least 2 conformers on the surface, the standing and the lying molecules. We also, by XPS, in that case, proved the fact that we had 2 contributions and not 1, and this would indicate that on the surface we had a titanium 3+ species, but also a titanium 4+ species, so one oxidized molecules by the contact with the surface. So we asked to our colleague, the people in Florence, to compute this, to simulate this system, and we understood that we could have different conformers on the surface of different sticking geometry, and all of them were more or less of the same energy, so equally probable, and none of them was going to lose the spin if they were isolated on the surface. So the reasoning and the rationalization of this, of all of this, was when we considered the packed layer. In the packed layer, we had a combination of standing, blue ones, and line molecules, and we could rationalize this quite puzzling STM pattern by DFT simulation, and these are the real images, in which we had that the pattern was actually rationalized by this quite complex cell. This was one out of 100 cells that the theorists attempted, and this cell could rationalize also the fact that we actually switch the molecules. So the line molecules, for example, here appear as a bright spot in the STM, also in the simulated one, and then when you reverse the bias, you see them as a dark spot. So this was a nice merge with the theoretical part, and also the theoretical part suggested that in the packed layer, we had an electron donor activity from the nearby line molecule towards the standing molecules, and this activated an electron donor from the standing molecules through the magnetic orbital to the gold surface. And that's why we saw also titanium 4+ oxidation state in our XPS spectrum. I mentioned this, so we had an array of spin alive, spin active, and no spin active state in our molecular pattern. So I mentioned and presented these results because these results were quite interesting in the superconducting point of view, because as soon as I mentioned at the beginning, as soon as we can couple a single spin with a superconductor, with the Cooper pair of the superconductor, if this coupling is effective, we can then produce a localized bound state that appears in the spectroscopy within the band gap of the superconductor. So this is a collaborative research that we have with the group of Sebastian Lott in Stuttgart that does some more than one low temperature or very low temperature STM. And on these molecules, on this kind of molecule, on the CPTI coat deposited on the lead-111 surface, we saw again that we had some raft in which we had standing and lying-oriented molecules. The nice part of that is that we understood that then the lying molecules was not producing any Shiva state in the superconductor, within the band gap of the superconductor, but the only molecules that were producing Shiva state were the standing ones, and we could also control the extent of coupling. This is because the standing molecules have the dz square orbital, so the magnetic orbital, which is directed towards perpendicularly to the surface, so has a higher energy match with the surface. Just very last minutes, just to show you in these few slides where we are now directed, so which is the next direction. As I mentioned, it's of course nice to probe Shiva state on the superconductor, but it would be nice also to have a way to controllably coupling the Shiva state to obtain, for example, topologically protected state. And then all my recent projects were on coupling, were on investigating quite complex molecules, also ionic compounds, in which the organic ligand was coupling the three different ions. So these kind of molecules are basically have a magnetism that has a spin frustration, meaning that each ion has an antiferromagnetic interaction between the other, but this antiferromagnetic interaction can not be satisfied at the same moment through the three system, and this leads to a double degeneration of the ground state that is pictured in this sketch here of the spin arrangement. These complexes are interesting also because their magnetism has a strong coupling with the electric field. So we can also switch between controlling the magnetism and the electric field response in these compounds. So I started with the help of the postdoc that was assumed for the project to investigate these two species, two spin triangular species. On your left side, you're going to see this triangle that is made by 3 cobalt plus ion, with each one having a spin equal to 3/2. And in this second half of the slide, you can see this spin triangle that is composed by cobalt plus ion. The investigation of both compounds, it's important because the two compounds have really different magnetic exchange interaction strength between the ions, so can give us in the future a feedback on which is the role of the surface on this exchange coupling. These are fragile systems because these are ionic compounds, so this is the main molecular structure, but you can see that we have a counter ion, so we cannot sublimate this system, and we let them spray on the surface by an electron spray deposition setup, in which we have a capillary, that capillary injected solution through 2 different pumping stage, the solution to the sample. This somehow worked out, and we measured the magnetism of both systems that, as you can see here, as soon as we probe the cobalt L3 edge for this compound or the copper L3 edge for this other compound, we have a different trend of the XMCD as soon as we rotate the sample and the molecular layer with respect to the external field. In this first case, we see that the more grazing we go, the higher is the signal. In this other case, we have an opposite behavior. This tells us that the magnetism of the molecule on the surface is intact, and also that the triangular plane of the metal ions is parallel to the surface, because in this case we have an easy plane anisotropy, so we maximize the magnetic signal as soon as we go closer to the plane of the triangle. In this case, we have an easy axis anisotropy, so we lower the signal the more we go grazing so far from the main anisotropy axis of the molecule. So this is just to tell you that we are going towards this investigation of multi-spin platforms from metal ions, but also from radical pure organic compound. This is a little bit challenging, but we are trying to do that. And before concluding, I mentioned that it has just started 1 month ago, a Marie Curie project on the that is controlled by us, that has as objective to form a covalent organic framework based on spin valence system, porphyrin based, connected to radical linkers that can perform an active magnetic exchange between these porphyrins. This is a really challenging project, but this is the next perspective for collaboration with this audience, I hope. So this is what I've explain and try to show you about molecular spin qubit. We can tune the spin coherence, we can tune the spin-spin interaction through the ligand, and we can also produce some Shiga state with the superconductor. With this, I conclude. I hope that you are not too much annoyed, and thank you for your attention.
Questions? Thank you.
I have a question. How can you use, you showed the molecule with titanium and the 2 rings of carbon. How do you use as a qubit? Because if it is making tunneling, the spin, means that this is an asymmetric two-level system.
And so in that case, we don't have the quantum tunneling things that I was mentioning at this. So what you saw concerning the energy barrier, the reversal
How
of
much
the
is this
barrier.
barrier?
This barrier depends on the molecule. It's 15K for the iron 4.
15K, small.
Yeah, small. So we
So
were
you have tunneling.
we were at 200 milli-K to observe this.
And you have tunneling.
But we have tunneling of the magnetization as soon as we have resonance, so aligned energy levels between the two states. There we have tunneling, otherwise not. And this is what the Stairs group tells you, that the magnetization stays constant until certain
How
resonance.
do you have this tuning? Because it looks very asymmetric, the molecule. You have a ring of 6 and one of 5 carbon.
No, but this is not a single molecule magnet. So the now I was speaking about the very first system, the iron 4 compound, so this bulky molecule that I was presenting at the beginning with the sensing tool. But this compound is just this has no hysteresis loop. So these molecules with one single ion with spin 1/2 system, they don't have any magnetic memory, but they are good for quantum computation application, for acting potentially as a qubit, because we all know that the superconductors are much better than.
The 2 states of the qubit is not spin up or down, but
you have a linear combination of all the phases.
All the phases. So
you have a linear combination in the block sphere, so for example here, of the up and down state. Okay, so the spin can be up or down, but you can the spin 1/2, but you can have a linear combination of these. The fact is that how long this spin retains that space. Yeah.
Asymmetric.
In this case,
it's asymmetric, so I suppose it is asymmetric.
Okay, it's asymmetric concerning the ligand, but the spin feature is it's a spin 1/2, so it's isotropic. Spin triangles are not isotropic, not all of them, but this yes. So the G value
the 2
more or less
of the qubit are the 2 fundamental, are the first and the first excited state of the 2-level system. Is it so?
It is the up and of course the up and down state. So it's the first and the excited state of the 2-level system.
It is making tunneling continues to.
No, so the coherence time tell us is that the spin information, so the phase of this spin that of course can move, is retained for 35 milliseconds. And this is a problem of any magnetic ion, also without the organic ligand around. Okay, actually, if you go find a magnetic ion on the surface, the problem is even higher because you have anyhow a crystal field that the ion sense because it is in a particular position on your surface. So also in that case, you have some asymmetry because you have a spin on the surface. Okay, but no.
You don't have a ligand field effect on this molecule.
We have
it's very small.
We have a ligand field effect, but it's very small.
Yes.
Yeah.
Regarding this molecule, I was curious. You showed this, the beautiful STM images with two different.
What we could do, I mean.
Sempre belle, per me. The two different kind of molecules, the standing up and lying one. And you said there is a point. I listen. You have two different oxidation states depending on the alignment of the molecule. This is the point.
So what we saw at the beginning, this was really a puzzling work for us. It took some time to understand the picture. So we saw this bias dependence. Okay, it was quite strange actually, and we saw by the XPS that we had the contribution, a titanium 3 plus contribution that we expected, and a titanium 4 plus contribution. So then the titanium 3 plus has also its satellite peak, but it was not enough to explain this second, the height of this second peak. So we knew that on the surface we had titanium 3 plus and some titanium 4 plus species. Okay, so this is something that we knew by the XPS. It's a nice skill because many STM people do just STM and cannot access to the oxidation state, to the average oxidation state. So this is I would say an important information. Okay, so what DFT people did is to compute the single molecule in different absorption way on the surface, and they found that all the arrangements were more or less equally possible, and also that in all the cases they hold the retainment of the spin. So they hold the spin. They didn't have a great loss of the great electron delocalization from the molecule to the surface or vice versa. They saw that just when they simulated the compact layer. So meaning the unit cell, because from this combination, they saw here that the standing orientation was performing some strong electron delocalization, like losing one electron really from the molecule to the surface, but didn't do that alone, okay? So it did it just in the compact layer because maybe of this effect of electron donation of this ring, of this nearby ring, which are electron rich, towards this central standing molecule. And this is something that we are now rationalize also on the synchrotron, because we have the magnetic response that comes only from the titanium 3 plus ion, because of course the titanium 4 plus derivative is not magnetic. And for example, we put this layer also on silver, and on silver the packing is different, and all of them retain the spin, and the XPS show just one component.
The work function is very different.
So gold is never innocent. This is what we got.
But how did you rule out the total or partial breaking of the molecule that can lead to titanium 4 ions alone?
You're right. So we can never exclude this, but it was quite now the lighter hit a little bit but you can see here, for example, that at the end here it just showed a couple of pictures, but we have had the complete set of data of STM data different biases, and DFT simulated images at different biases for exactly this cell, and we had a very nice match between the simulation and the experimental curve. And what synchrotron is telling us, I haven't shown this data, but what synchrotron is telling us is that at least the titanium 3 plus molecules have the right TMCD signal, so they hold their spin state. So this is what we are sure about. Yeah.
Thank you for your nice seminar. I have a general question. So, what is the mechanism that you employ to, or you would intend to employ to create a superposition of states in this kind of qubits?
Not a question for me, actually. So, no, it's time. So I cannot really.
No, but, so it's just a curiosity because with the light, it is very difficult to produce a coherent state because you cannot change the spin with the light, or you can change the spin with an intersystem crossing. So you have something that is can destroy the coherence. I mean,
Yes,
this is just a
one of the
curiosity.
big challenges.
It's
So the point is that everything can destroy the coherence of any superconducting system. Also,
no, I was
descent
looking at this qubit. I mean, this qubit has no hysteresis. Or
no, this qubit is
and no superconducting surface. Is it?
No.
Okay.
This is not a superconductor, but as I showed before, on the superconductor, we excite for the standing molecule, we produce localized Shiba state.
Okay.
Yes. So the way, but it's not done by me, okay, in which these spin qubits and also molecular spin qubits are controlled is by coherent pulses of magnetic field and electric field. So by this eco-resonance scheme, they can controllably switch between the up and down state and keep track of the pace of the spin.
So no light is involved.
At the moment, no light is involved, but this is part of the new evidence.
Another
As well as
curiosity.
the cis effect that
So these molecules are evaporated by electrospray deposition.
no, these are just sublimated from
Okay.
temperature.
And
So you open the valve and you let them
Okay,
fly
okay,
because
so
their mass is quite
vapor
small.
tension,
Yeah.
classic.
Yeah.
And you showed us electrospray deposition.
The setup for the electrospray deposition. Now I don't have here a picture.
But you
this
control the
presentation.
density of these molecules. So are
on
they
the side,
closely packed
yeah.
or just because there must be qubits? They cannot be closely packed, I suppose.
They cannot be closely packed, but I mean, also in the crystal, they are closely packed. Okay. Also in a frozen solution, they could be closely packed. Of course, for example, the phonon modes are also an additional decoherence source.
Sure.
For example, I don't have here the molecule that I mean, but our chemists produce an organic ligand without hydrogen because the vibration of hydrogen is a high source of decoherence. Okay, so they produce this ligand base of carbon, nitrogen, and sulfur atoms, coordinating a copper plus ion. This is another promising spin qubit, and the coherence time was really poor. And this was maybe due to these phonon modes that you have in the crystal. So it is really of course challenging, but I would say on surface you have the additional
more than phonons. At those temperatures, it is more the conduction electrons than the phonons.
Yeah.
Much more.
But
200 milli-K, it is electrons.
Or 200 milli-K, yes. So the surface itself could be a decoherence source. For example, people doing ESR, so EPR, STM, Korea, they are doing, they are probing single ions or spins molecules on top of an MgO layer, because this is a much stiffer substrate. So basically, they don't see any spin signal on gold or normal metal. So a challenge, for example, is also to deposit molecules that have, from a chemical point of view, a challenge for me is to create a spin qubit which has a ligand that really protect well from the environment, from the surface, your spin. But these ligands usually are not easily accessible by the STM tip, for example. So if you want to do it, but of course the surface can be integrated.
Thanks a lot for the nice presentation.
The electrospray. Beg your pardon.
So the electrospray, so
Okay.
which was the question because so this is the electrospray setup. This is just a sketch. Maybe later I can show you the real spray that is bought by molecular LT. So it's not so expensive, I would say. Few €1,000, no, because it's not the one that occupy a big room with tough seams in between to check the mass. This is really expensive, but the compact one is not really expensive. You just have, no, here is not. You just have a syringe here with your solution inside, and then you have something that pushes the syringe, and you can control the rate of this pushing, of this injection, and you have the solution pass through a capillary that has a certain voltage that you can tune with respect to the entrance to UHD. Then this voltage let the drop to be deformed a bit in order to activate the spray towards the vacuum. Of course, here you have turbo pumps and scroll pumps that pumps down let the solvent escape, hopefully escape, and we go from ambient pressure to 10 to the minus, high 10 to the minus 8 or low 10 to the minus 7 during the spray. So it's quite efficient.
Also, without a mass spectrometer, are you sure that your final product is a single molecule?
So we check that by XPS.
Okay.
So by XPS, I haven't shown you the XPS data, otherwise it would be too long, but the XPS tool is really important in this respect. Because you can check all the signal concerning your molecules, you can do a certain kind of spectroscopy.
Can I ask you a rate of growth of this machine? So how much time I need to have a monolayer, for instance?
For example, for these spin triangle molecules, with a solution with concentration 10 to the minus 6 molar, it took like half an hour the position to get very thinly monolayer. The point is that, first of all, you have to use polar solvents. So a polar solvent wouldn't work because cannot be polarized by the voltage. So the drop cannot be deformed and cannot spray inside. So you need to use water, but water is not nice, never nice. So methanol or something that is polar, actually. And this could be an issue sometimes in chemistry because the organic ligands are soluble most of the time in a polar solvent. But you can use mixed solution.
Okay.
But you don't protonate.
Thanks a lot.
Welcome.
Mettiamoci d'accordo. Qualcuno che dirige il traffico, queste domande, se no qui.
Allora aspetta che ce l'abbiamo avanti.
C'è. Possibile qui che.
Dai.
La memoria.
Yeah, I was also curious about the sample preparation. In the sample you mentioned that you had like several nanometers thickness for some samples, but you mostly study like one monolayer. And if you change the coverage, do you see, of course, changes that are coverage dependent or not?
So we have different preparation setup. In the main platform that I showed you, we basically study one single layer or a few layers. don't contaminate too much the systems. And also because we do XPS, we do STM, so we don't need to do the thickness. Then we have, of course, microbalances to check the rate, to have a feedback on the deposition. Our method is to deposit less time as possible to STM, to decide on the STM base which is our monolayer coverage. Then we get for that surface an intensity signal reference for the XPS side. So we can check also when we grow multiple layer, we can check the ratio between the signal that comes from the monolayer with respect to the, so we can control this. And then we have, when we really have to go like 200 nanometers thick films, then we have dedicated chambers that, in which we can sublimate more. And then but most of the time we put this sample in air, because most of this, except the titanium compound, but all the other structure that I showed you are air compatible. So they
For the experiments, you usually use one monolayer.
Yeah, the extensive experiment, we usually do one monolayer for checking, because we are interested to the interaction between the single layer and the surface. Yes, and that's why we keep the vacuum.
Very quickly, just a curiosity, because most of your results concern like self-assembled molecules, self-assembled layers on the surface. But now in the last project, you are moving towards covalently coupled molecules.
Yeah, that's why I presented to you this.
Yeah. You actually showed the radical linker. I don't know, do you already have preliminary results on these systems? Do you know if it is stable upon annealing on the surface, or you still need to start?
We still need to start.
Okay.
And at the moment, there are chemists who are synthesizing this Verdasil compound.
Okay.
But we saw that this triangular radical system have been sublimated by Japanese groups. So on the surface on gold, and they saw the condo fissure also. So it seemed that they can sublimate. They never let them sublimate with these halogen derivatives. So the inner part has been done, but this halogen derivative has not been deposited. So this is the first task. And then we have to activate the Ullmann coupling between this Verdasil compound and the porphyrin units. And in my opinion, so the most challenging task will be to really create an homogeneous layer, because we could have also, I guess, cross coupling with homo coupling, so we can couple the same species. We are now planning to use different halogens, but for sure we will start from the deposition of both compounds. We are going to study first this species, then this other. Then of course we did a lot already on board, so quite confident concerning the deposition of porphyrins. But we are going to study if we can couple this single object to the Verdasil, and which is the success rate, and the additional same level challenge for me is to really couple magnetic spins in the porphyrins through this channel, because porphyrins can, ions in porphyrins can barely couple in this configuration. So this vanadil species has a magnetic exchange interaction which is in the order or fraction of EV. So it's very weak, but it's really good for doing C0 gates, so quantum logic gates. So it's good for that purposes. Of course, if we change the ion with cobalt or copper, we can try to maximize this exchange interaction. But as soon as we go more far apart between the two species, the exchange interaction will either pass through something that magnetically connected these two ions. That's why a radical would be important, or through the surface. This could be also the case. We would need a very good STM to do that.
Okay.
I have a question on the coupling of this molecule with the LED system. That one.
The CP,
Yes,
I call it.
previous part of the. Because what I found, what I found interesting is that you could couple this molecule with the vortex states of the superconductor. So I think that's something which is missing, because on one hand you have this STM measurements in which you show that the molecule has an arrangement in the surface, and you study this. On the other hand, you have this magnetic measurements, and you miss the microscopic part of the system. So you measure macro measurements, you have micro measurements, but in the middle there's something which is missing. For example, my question is, did you perform on this system differential conductivity measurements by the STM, for example? You should be able to see these vortex states, not only the formation of these vortex states, but also the movement of these vortex states. For example, if you use a magnetic tip, you could even follow these vortex states, and you could even probe maybe all the states related to the coupling of the molecule with the lead as a function of the magnetic field. There's something missing in this
I would
description.
love to do that. So we need a STM couple to go down. So down the critical temperature of the superconductor. So below 7K. Yeah.
Yeah, but it should be easy for you to perform STS maps of these systems and verify that the pattern of molecules that you deposit on top closely follows the vortex states of your systems. I guess I don't know, an expert on that.
With our STM setup, we cannot do that. We cannot even use spectroscopy. The point is that in the variable temperature setup from Omicron, you have helium flow that does cool down the surface. So this is good for stabilizing molecules, but you have the tip. The tip is basically at high temperature, not I don't know which, but at higher temperature. So we cannot really take reliable STS signals, because you will never end up on the same point of the molecule, for example. And concerning the images of vortices, we will need to go below at least 7K to see them. And we can go just between 30 and 40K. So we really cannot do that. And we performed just this few STS experiment in collaboration with the Barcelona in Stuttgart. Of course, we have the full access to that instrument. But yeah, so this is basically the limit of our STM capabilities. But it's feasible, so if someone wants to do that.
You would need the magnetic field as well.
Trying to get you.
We understand.
Yeah, we need to be very low in temperature and to have the magnetic field. It's not
The fields are not so high.
no, not
Below.
yeah.
Yes, well, that's not so.
Yeah.
Please, Giuseppe.
There is a question?
I was curious because we have put a lot of molecules with Stefano and Fabio on metal surfaces, often metal surfaces. And when we put large conjugate ligands on metal surface, we always invariably see some degree of metallization of the ligands together with the surface, and this influences very much the magnetic behavior of the center. Of course, you can treat the magnetic center as something that you can think as some isolate mediated, weakly mediated by the surrounding, because you want to couple, for example, with your substrate, with your superconductor substrate. But is it always correct? For example, when you have a second layer on top of the first layer, you see an enormous difference because the second layer is decoupled, the ligand is decoupled from the substrate.
Yeah.
It is correct to average out everything without keeping explicitly in mind that your ligand is metallized on the surface. Have you thought about this and find this, that sometimes you must explain something because of the mediation of the ligand between the metal and the magnetic center, and sometimes it is not important?
Yeah, so this extremely depends on the ligand. For example, I showed before terbium PC2 molecules that molecule that had two phthalocyanide ligands, and phthalocyanines interact a lot with surface.
We know very well
always
because
have
we have put the ruthenium
metallization.
phthalocyanine on
Phthalocyanines are-
everything.
yeah. Exactly. Porphyrins, for example, are very good decoupling systems because at least the tetraphenyl
Because of the
porphyrin, because you have the
rotating
phenyl.
Yeah.
So phenyls flatten out the surface, but not completely unless you anneal or you do something that is thermally activated. But they flatten, but they keep the metal ion a little bit decoupled, geometrically far apart from the surface. So in this respect, porphyrins are better than phthalocyanines, but this also depends on the magnetic ions for us, because, for example, for this vanadium species, we can have the upstanding or the downstanding configuration. So, for example, also in a work that we have done with Sebastian Lott on lead 111, concerning, maybe I have it here, concerning the WOPC compound, if we were on the standing, on the upward position of the vanadium, so of the spin center that is rotated here, we didn't see any Shiva state. In the down configuration, we always saw the Shiva state. Then as soon as they push the tip towards the vanadium system, they activate more the interaction with the surface because they were basically bending the vanadium center. So the vanadium center, so the spin 1 system was closer and closer to the surface, and you could induce some Shiva state, even though initially in the vanadium up case you didn't have it. Okay, so the combination of the ligand and the ion, and the magnetic ion, of course, play a big role with the surface interaction, I would say. And what is important depends on what you are doing. For example, when I spoke about the thick layer of iron 4 single molecule magnet on superconductor, there we were looking at a sensing mechanism, sensing the local field that extends for microns with respect to the surface. So we basically don't care what the single layer is doing. But when you have to really see the interaction between the single ion and the surface, you really need to control which is your single layer. I don't know if I answered the question.
Yes. Thank you.
Other questions? Otherwise, we thank Giulia for the very interesting seminar. But-
Salve. Non vi ho annoiato troppo, però mi avete fatto